So, how many of you guys think that every time we want to study free fall, you have to make this big table of numbers to figure out what's going on? Would that be really annoying? That would be really annoying, right? So we don't have to do this, but I wanted you to do this to help you see why we have these four crazy equations. These are called the kinematic equations for constantly accelerated motion. Galileo came up with these. They only work in one special case. What's that special case? When you're undergoing what? Constant acceleration, which includes free fall there. And he didn't call them this, but we call them the TNEMs, the nifty equations of motion. They are as follows. Equation 1 is VF equals VI plus AT. Equation 2 is delta x equals VF plus VI over 2 times t, or VI plus VF. It doesn't matter the order. Equation 3, that's a big one. That's a Galileo one, is delta x equals VIT plus 1/2 AT squared. And then equation 4 is VF squared equals VI squared plus 2a delta x. I think by the end of this unit, you'll actually have these memorized like me, but you don't have to memorize them forever. Let's unpack this for you. Each of these equations has 4 out of the 5 variables when it comes to constantly accelerated motion, where a is for acceleration, delta x is your change in your position, your displacement, VF is your final velocity, VI is your initial velocity, and t is equal to the time interval of motion. Now notice I created this grid over here, and I came up with this because I actually found it very helpful for my students when we start looking at free fall problems. Notice that in each of these equations, there are 4 out of the 5 variables when it comes to free fall. One of these is always missing from these 4 equations. So for example, in the first equation, VF equals VI plus AT, notice that it has A, it has T, it has VI, it has VF. What does the first equation not have? It is missing delta x. That's why it's got a little sad face. It's not complete. Oh. So how's this helpful? Here's how it's helpful. When we look at a free fall problem, it's all about breaking down your knowns and unknowns. This is your toolbox of equations to help you attack these ideas here. So once you break down all your knowns and unknowns, that's the hardest part, is reading the problem, sketching it out, listing all the knowns and unknowns. Then you just look at your toolbox to get the job done. If you need to pound nails, use a what? A hammer, right? If you need to put in screws, use a screwdriver, etc., right? You look kind of weird if you're using a banana, right? This is going to help you have success there. When you look at this, how many of you guys think, man, this is a lot of weird, nerdy math? Yeah? Ha! I tricked you. You actually used 3 out of the 4 equations on our table. Did you know that? Let me show you really quick. You actually used all 4 of these equations. You didn't realize it. Check it out. Equation 1 is VF equals VI plus AT. What's the initial velocity? The starting speed was what? Big fat 0, right? Acceleration was -2 times the time, right? So 2 times 1 is 2, 2 times 2 is 4. Use equation 1. Ha! I tricked you. Look at this. You got the delta x. You actually used equations 2 and 3. Did you know that? You didn't even know that. Equation 2, you don't have to write this down. I'm just showing you that you actually use these. Delta x is equal to VI plus VF over 2 times time. The initial velocity was a big fat 0. Final velocity was this column over here. So in other words, it was the average velocity, actually, right? This is just the average velocity times the time. You just multiplied column 1 by column 3. You actually used equation number 3. You didn't realize that. That's a biggie. We use this one all the time. Delta x equals VIT plus 1/2 AT squared. Initial velocity was 0. That drops out. Half the acceleration is -2, which is -1, times the time squared. 1, 4, 9, 16, 25. Okay, don't worry about it. You used them. You didn't even realize it. Ha! So those 4 equations, how did Galileo come up with? Equation 1 is just, this one actually kind of makes sense when you look at it. VF equals VI plus AT. You take the basic definition of acceleration, which is change in velocity over time, VF minus VI over t. You rearrange the cell for VF. You bring the t up, and then you add VI to both sides. So this one, if you look at it, actually makes sense. How fast you end up going, VF, is equal to how fast you were going, VI plus your rate of acceleration times time. Equation 2. You take the definition of velocity, you solve for delta x. You take velocity as your change in position over time. You bring the time up. If acceleration is constant, you substitute in for delta v. You do a lot of algebra magic. Boom, you're done. Next, number 3. You do lots of nasty stuff. This one, you take equation 1, you substitute into equation 2, you eliminate for VF. And then you have to combine like terms, and you get that one. So it's just algebra there. We're not going to worry about the details. This one is not very intuitive. And the last one, you have to take equation 1, you put it into number 2, and you do that FOIL thing, the first, outside, inside, last, and you combine like terms, and you get the final one there. So in the end, it's not using algebra, it's understanding the motion there.